Nice. Okay, so the last thing in your notes we have is plate tectonics, yes?
And Pangea.
Right? So we talked about how we had Pangea to start with, right? And how we have proof that the continents at one point were all touching, right? The first piece of proof was that jigsaw puzzle, right? That you guys pretty much all did in elementary school. Yes, maybe. Right? Where you took pieces and you cut out each of the continents and you tried to figure out how they go together. And they pretty much almost go together perfectly. And I say almost because there is a little bit of an overlap. A little bit. Just a little bit. Right? Have we done this yet?
This one, yes.
Okay. What are you confused about?
If everything is at one place, what was on the other side? Just pure water.
So everything else is water. Yeah. Okay. And the way that you can figure it out is it all comes when you come to figure out what the Earth was like back in the day. It all comes down to fossils, right? Because the second thing that you're going to look at are the fossils, right? If you want to say that most of the Earth was covered by water at some point, look for marine life fossils on land. Because that means some of the water has gone away or the land has come up and now there's leftover fossils, right? So the fossil evidence is that if we look at different continents, similar, if not the same fossils show up on different continents, which is near impossible unless they were all touching at one point. Because some of these are not going to cross over vast majority of the ocean, okay? The fact that we have geologic evidence, right? Things like mountains are made up of the same thing. And when you put all the continents together, they pretty much line up in a straight line, right? Because remember, mountains are made from that uplift that happens inside of the crust, and then they come together and one gets uplifted, and that's how you get a mountain, right? Then you also have, what are those things called? Variations. And what are they made from?
Glaciers running along the thing.
Exactly, glaciers running along. So we have glacial evidence that a glacier went across Antarctica, part of South America, part of Africa, part of India, and parts of Australia. Okay? The only way you could do that and have it in those particular locations is if all of the continents were touching at one point. Okay? So there are your 4 things of proof that Pangea was a real thing. That the continents at one point were basically one giant blob. And because of crustal movement, right, they ended up moving apart from one another. So let's talk about that crustal movement. Okay? So you have the Earth's lithosphere. Right? We all know what the lithosphere is made up of.
Wait, lithosphere is the blue one on the ground.
Yep. Okay. And it's broken into about 24 pieces called plates, which float over the asthenosphere and are in constant motion. Is it?
Yeah.
Let me see if I can change it real quick. No. If it's hard to read, I'd rather know than not know. Here's the only problem.
Change the yellow.
Yeah, well, this is the problem. Right. And then, see if I can go all the way down here, just in case. We'll go with white. Save. Come on. This is the only problem, because I don't know if the pictures are going to line up now. All right, so basically, guys, the lithosphere is broken up into a whole bunch of different plates, right? And those plates end up floating on top of the asthenosphere. Okay, let's go back. Here we go. There we go. All right, so they float over it and are in constant motion. Okay, this is part of the reason we had the continents the way that they are now. This is why we end up with earthquakes and tsunamis and all of those fun things, because you have those plates, which if you look on page 5 of your reference table, which you all have out on your desks anyway, okay, we've been referring to this specific one for this entire chapter, even though we haven't really learned about it, right? We have all of these different plates that are there, and it has to do with that whole, what is that called? What is this called? Convection currents, guys, come on. You have our unofficial final on Monday and Tuesday of next week, right? Can't say the word final, right? So it's constantly happening inside, which then allows the plates to move in those directions. And depending on if they are hitting each other, is one subducting over the other based on density? Are they running into each other? Are they moving apart from each other? Okay, it's based on the convection currents underneath. It kind of, since they're floating, it's moving with the current underneath. Right? So here we have a subduction zone. Right? Actually, we have both. We have the subduction one that's going this way, right? One of it's going down under another. And then you also have a divergent, which means that they're moving apart, which creates a ridge here, okay, which allows that magma to come up, harden, and move apart. Right? So here's the first type of plate boundary. It's called a divergent boundary. Okay, a divergent boundary means to move apart, which is why if you look at page 5 of your reference table, the two arrows are moving apart from one another. Okay, since they're moving apart, you end up with a ridge, and that's basically a volcano at the bottom of the ocean, right on the oceanic crust. Okay, this allows lava to come out of that particular area. So if you're looking at page 5, you can find different things like the mid-Atlantic ridge. Okay, and that's where you're going to have a divergent boundary. Okay. The thing is, you have to understand about divergent boundaries, and everybody's looking at me for a second, right? Right? If the lava is coming out of a crack here, it's going to come out and move to both sides. Right? So it comes out and it creates new crust on both sides. Right? As it does that, the further away you get from the crack, the older the pieces are. So the further away you get from that ridge, the older the pieces are. Because what's happening is, as it moves up and creates these two, the next group comes up and moves those two along, and then moves the next two along, and so on and so forth. But here's the thing. It's like a mirror. The two that are made up of the exact same stuff, and they're made up at the exact same time. Exactly. It's a pattern, okay? So when you're looking at divergent boundaries, okay, you're going to look for the same. If they say to you, like, what should the pattern be on the left side if this is the pattern on the right? It should be the exact mirror image, okay? So this is what happens, right? You have that partially melted lava that comes up, or that magma that comes up, right? And then it splits apart. So that means the pieces that are on the edge here, this piece here and this piece here are the same age. They're made up of the same stuff, but compared to the rest of it, they are older. Okay? All right, so this is what it looks like in real life, under the water. Okay, this is always fun. You can see a lava flow that got lifted up. Okay, here's just some fun stuff. We don't really have time. Okay, so you have a convergent or a subduction boundary. This is where they hit into each other. And there are a couple different versions of it. The first one is when you have an oceanic versus a continental. So when you have the oceanic crust hitting into the continental crust. Okay? Based on who is more dense, that is going to be the one that subducts. That's going to be the one that goes under. So it's completely and totally based on density. How am I going to know which one's more dense?
Which one's deeper?
Nope. How am I going to know? If I say to you guys, this is an oceanic continental plate boundary, how am I going to know which one's more dense?
Reference table.
Exactly. It's in the reference table for you. We'll find it, find it, find it. You guys all have your reference tables out. Right? You got to find it. That's your job. Come on, you guys should know this reference table pretty much inside out at this point. Blair found it.
I think oceanic crust.
Where'd you find it?
Page 10.
So page 10 of your reference table.
Where it says density, it says 2.7.
Top right-hand corner, it says oceanic crust. It says granitic versus basaltic, right? And it says the density there as well. Make sure you guys know how to do this. So yes, the oceanic crust is a little bit more dense, so it's going to be the one that subducts down over the continental crust. Okay? Right? How you get all these fun things, explosions. Right? We just don't have time. Okay? If you have an oceanic versus an oceanic crust, so if you have two parts or two plates in the ocean, oceanic versus oceanic, okay? You still have one's going to subduct and one's not. You're going to have a trench here, right? What you saw before was the trench that people were walking through, okay? It's basically a giant hole. Okay? Happens all the time. One time. Okay, if you have continental versus continental. Continental versus continental. It's going to result in orogenesis. Okay? It basically is when the continental crusts hit and they form a mountain. It's like they're fighting with each other. They push up against each other, and eventually neither one wins, and it pops up like a mountain. Okay, that's orogenesis. All right? So when you have one continental crust hitting another continental crust, and eventually it doesn't go anywhere, right? So where does it end up going? Up, in creating a mountain. Okay, so that's part of it. You're getting uplift, all right, and you get mountains that way. Question? Go. Okay. So you get that uplift, and it creates a mountain. Here's continental versus continental. Okay. The other thing is that it slowly has moved the continents because of the fact of the way that they move. Right? It's pushing them closer together. I don't know what happened there, but okay. Right? So the Indian plate is moving into and eventually will subduct completely, and the continent of India will disappear. Okay? Because of the fact that they keep subducting. Okay. This is how we got the mountains. This is such a pretty picture. Remember water was really pretty? Right? Then you have transform boundaries. Okay. Wow, where did that go? I saw words. Okay. So this is mostly going to occur along the floor in areas called fracture zones. All right. So a transform boundary, they're going to rub up next to each other and going in opposite directions. Okay. So what do? Right? Transform boundaries. Right? Their symbol is going to be where you have one going in one direction and one going in the opposite direction. Did everybody see that on the reference table? Right? Everybody sees that on the reference table, page 5? Guys at home?
You.
Good. Okay. So here we have, right, I don't know if you guys can see it, right under the R. Oh, we could just do it that way. Right? Here's all the transform boundaries. So you have one moving in one direction while the other moves in another. But at the same time, you're also having a divergent right here where it says oceanic crust with the white arrows. Okay? It's just the way that all of these plates are next to each other. Right? And if you first have to figure out if you have a divergent versus a convergent plate boundary. And then what are they next to? Right? So here we have a divergent plate boundary up here, but you also have it next to another divergent plate boundary. But this part of the boundary is moving towards the right, where this part of the boundary is moving towards the left. So you end up with almost like a scraping as they move by. Okay? And it breaks up, basically, and it looks like this. Okay? You can see the trench. You can see how it's breaking up, and as it moves across, it's rubbing it up against each other. Okay? You end up with fences that get broken apart. Right? All right. So here's what's important for you guys. All right? This is all page 5. First of all, transform plate boundary is look for the arrows where it's one over the other. So when you're looking at it, you're looking up down here by the Scotia plate. Okay? You're looking up here by the San Andreas Fault, right, which is in California, right? For divergent plate boundaries are going to be any ones of them that the arrows are going away from each other, right? So that's where we're getting newer material coming up and being created through those lines. And then you have the convergent ones where they go towards each other, okay? That's going to be here. The subducting one is going to be the one without the little rectangles on it. Okay, that's the one that's going to go under. So here, the Nazca plate, under the Peru-Chile Trench by South America, right? The Nazca plate is the one subducting under the South American plate. So technically, South America is slowly moving to the left. Okay? I mean, it's not going to be... right? So you're going to look at the Mid-Atlantic Ridge if it has to do with North America, right? And the whole plate is moving northwest. So let's look, right? We have the Mid-Atlantic Ridge, right? And you see how it's diverging this way? This tells me that this whole plate is moving in the northwestern direction, okay? So the continents will not look exactly the same in a million years. They're not going to be in the exact same place in a million years. Okay? All right. So that is pretty much one other thing actually I wanted to tell you before we move on to the next chapter is actually about magnetism. Okay? Yeah, but also I've seen this in questions before. And this is what I was telling you about actually before. Hold on, where'd it go? This picture here. Okay? And I'm only going to stay by the computer, guys, so that you guys at home can see it. So here is where the magma is coming up right, and creating these different sections. So the white section here, right, is different than the red section, because what ends up happening is the polarity actually on Earth will reverse. And when it reverses, it creates a different version of it. It's the best way to explain it. So you see how over time now this red boundary came in, or this red part came in. That means this one over here is the same age as this one over here, and they are the oldest because of the fact that they are furthest away from the ridge. Okay? Same thing here. It just keeps switching. So it almost looks like tiger stripes. So over time, the crust is going to look different. It's almost going to look like, okay, so these two parts are the same and the same polarity, and then it switches, and then it goes back, so on and so forth. But I wanted to show you this picture because of the fact that I've seen this show up several times in practice questions. Okay? You guys good? Awesome. Save it, yes. Okay. Pretty much.